welcome to my today's class. So, my today's class, we are going to be doing simple harmonic motion. I'm going to be taking its definition. I'm going to be doing some proofs of maybe I'm going to be doing a proof of the maximum velocity, linear velocity, acceleration, and all of that. But first off, let's take the definition of a simple harmonic motion. Now, what does the word simple harmonic motion mean? Simple harmonic motion is a periodic motion. First thing to know, simple harmonic motion is a periodic motion along a straight line. Simple harmonic motion is a periodic motion along a straight line in which the acceleration of the motion is always directed towards the fixed point, and that fixed point is what the center of the motion, and is directly proportional from the displacement of the motion from the equilibrium position. That's what the word simple harmonic motion would mean. So first of all, let's say simple harmonic motion is a periodic motion. That's the first thing you should note. Simple harmonic motion is a periodic motion. Now, what is a periodic motion? Maybe I may have. Now, a periodic motion is a motion which takes place or which occurs at a regular interval. It occurs with respect to time and occurs at a regular interval. For instance, now if a car should travel, now this is not on the based on simple harmonic motion, but if a car should, I'm just explaining periodic motion. So if a car should travel 2 meters per second, 2 meters per second, this is the speed of the car in 1 second, and then travel 4 meters per second in 2 seconds, and then travel 6 meters per second in 3 seconds. Now this is what I mean by a periodic motion. A motion which occurs at a regular interval. And the car travel 2 meters per second in 2 meters per second in 1 second, or yes, in 1 second, and then 4 meters per second in 2 seconds, and then 6 meters per second in 3 seconds. Now you see what happens here now. You travel to, and the interval between the speed at 2 meters per second, while for the time we're having 1 second separating each of the time. That's what we mean by a periodic motion. That's what we mean by a periodic motion. And also, a simple harmonic motion is a motion which occurs along a straight line, whereby the acceleration of the object is being directed towards a fixed point, which is the center of the motion, and directly proportional to the displacement of that object from the fixed point. Now we have some few examples of simple harmonic motion, which I'm going to list down here. We have some few examples of simple harmonic motion. One good example of simple harmonic motion is your simple pendulum. Though I'm going to take just two. I'm going to explain just two here, and I'm going to move on to the word we're proving. So we have some good examples of simple harmonic motion. I told you the first one we are going to have our simple pendulum. Simple pendulum. This is an example of simple harmonic motion. Now, our simple pendulum, what do you have for our simple pendulum? For our simple pendulum, we have a fixed end here. This is our fixed end. And then we have a pendulum bulb attached to this fixed end. We have a pendulum bulb attached to this fixed end. This is the pendulum bulb. We have a pendulum bulb attached to the fixed end, and here now S here is equals to 0. Why is S equals to 0 here? Because the pendulum bulb is at rest. It's only displaced, but it's at rest. And we'll call here, since the pendulum bulb is at rest, we'll call it the equilibrium position or the center of motion. We call it equilibrium position or the center of motion. Please note, this is the equilibrium position or center of motion. So let's take for instance now, this object is then being displaced through a distance of x at an angle of theta. This pendulum bulb is displaced through an angle of theta and a distance of x. So this is distance of x, and at an angle of theta, the pendulum bulb is displaced. Mean something like this at an angle of theta. Pendulum bulb is displaced through a distance of x and at an angle of theta. Now there is a force which tends to pull this pendulum bulb backward. When the pendulum bulb is displaced, there is a force which tends to pull the pendulum bulb backward towards the equilibrium position. And that force is known as the Westernian force. The Westernian force tends to pull the object backward towards the equilibrium position, and note it goes beyond the equilibrium position. That force which keep the object to go beyond the equilibrium position is what we call inertia. Please note. When the object is being displaced through a distance of x, there is a force which tends to pull the object backward towards the equilibrium position, and that force now is what the restoring force. Its arc tangential to the arc created by the distance displaced by the pendulum ball, and its arc perpendicular to the string of the pendulum. Its arc perpendicular to the string of the pendulum, and the arc tangential to the arc created by the distance displaced of the pendulum ball. Distance here for the equilibrium position here is 0. And note, when being displaced and released, the force which tends to pull the object backward, when the object moves backward, when it falls back, it goes beyond its equilibrium position. That is, it swings towards its direction. That means the object comes here, goes beyond the equilibrium position and swings towards the direction like this. So the pendulum bar appears, so it goes beyond the equilibrium position and swings. So now the force which tends to put the what keeps the object moving after it passes beyond the equilibrium position, what we call inertia. That is what keeps the object moving to go beyond this equilibrium position. So this is what the restoring force. So these are a simple pendulum work. So as the object swings towards direction, it also swings backward due towards gravity and the tension in the string. Notice there's what tension in the string. Now when the object swings towards this direction, it swings backward. That is why it oscillates. It oscillates continuously like that. Now what pulls the object backward is tension in the string and gravity. Please note that will pull the string backward and then swing forward again, and then being pulled forward again by the restoring force. So let's take another example of simple harmonic motion. We have our spring. We have our spring. Another example of simple harmonic motion. We have our spring. We have our spring. And a spring is like this. This is a spring. This is a spring. Now let's assume this is a spring. This is a spring here. This is a spring where no load was being attached to it. Let's just assume this is a free body diagram. This is a spring where no load is being attached to it. But when a load or a mass of body is being applied to this spring here, it depresses. It depresses here. So what happens here? Let's take another diagram. So when a load is being attached to this spring, it depresses. It depresses. So let me say that load of mass then is being attached to the string, it depresses. So let's just take a trace from here. Let's take a trace. So this should be the first equilibrium position of the spring. This is before a load was applied to the spring. Now this spring is at rest, no force on it. Why this would be the second equilibrium position where the object is being displaced. Because when the mass is being applied or being put on the spring, it depresses downward. And when it being depresses downward, now it becomes it has a new equilibrium position, which I wrote here as E2. It has a new equilibrium position because when the spring depresses now, it stays there. It's only when you apply force to it that it begins to compress, then depress continually, it begins to oscillate, it begins to enter into motion and oscillate. So this is the first equilibrium position. And this is second equilibrium position. Now the spring depresses to a distance of y. To a distance of y. You can also use x, but why we use that? Because it's a vertical distance, and we use x for horizontal distance. Please note, we use y for vertical distance, and we use x for horizontal distance now. And then the force which tends to pull this backward also a restoring force here. Also have a restoring force. Note that I always act in opposite direction. The spring depresses downward, while the force upward, which tends to pull the spring back to its former equilibrium position, and though it goes beyond it, and make the spring to compress. So I'm going to take this to example. Now I'm going to consider simple harmonic motion and a periodic motion. So in the circular motion, I'm going to be considering simple harmonic motion on a circular motion. Now let's consider a cycle. We're having a cycle here. So this one is not bad. So let me bring it down a little bit. So let's consider we're having a cycle here. Let's consider we're having a cycle. Sorry, I don't know how to draw. So part on me. So let's consider we're having a cycle like this. So it's not so bad, but see how we need to come out. So let's consider a cycle here like this. and it has the center here, which is what we should call cosine. Let's call this point A, point B, point D, and point E. Now let's consider simple harmonic motion on this circular motion. Now take for instance an object is moving. Let's consider this to be like a circular board. Now if this diagram, let's consider it to be a circular board. If this object begins to rotate from this circular board, know that the object is not simple harmonic now, because the simple harmonic motion is a motion on a straight line. Now the motion may be periodic here when it comes to a circular motion. The motion may be periodic, but the motion is not simple harmonic. So if the object moves round this cycle continually, the motion perform like, what would I call it now? Should I say partial simple harmonic motion? But there's what they say about this now. Take for instance now the object moves around this circle, and then let's say the object is somewhere here. Let's call the object Q, or let's call the object moving N. Let's take for instance the object is somewhere here now. Note for simple harmonic motion, they say the object's acceleration is always directed towards a fixed point, which is the center of the motion. So that means that at any point this object will be in this cycle, its acceleration around this cycle will always be directed towards a fixed point, which is what the center of the motion. And for this, the center of the cycle, its acceleration is always directed towards a fixed point, which is what the center of the cycle. So at any point, the object appears to be here. Same thing, at any point in motion, the object appears to be, the acceleration is always directed towards a fixed point, which is what the center of the motion. Let's bring this, let's take this off, which is what the center of the motion. So let's say this is it now. The acceleration of the object is always directed towards the fixed point, which is what the center of the motion. So we call the object what? N. So now, for the object to perform, I told you that the object like this just moving around the circle is not performing simple harmonic motion. It performs simple harmonic motion partially, because though it obeys some rules but not completely all the rules. So let's assume that this diagram here is to be a reflective surface now. So know that the shadow of this object now will be projected on the horizontal surface. The shadow of this object now will be projected on the horizontal surface now. Now this is the visual image of this object will be the one performing the simple harmonic motion, because now it performs simple harmonic motion along a straight line. It obey the first principle. Secondly, now it occurs at a regular interval moving outwardly from C. It occurs at regular interval. It will be the second principle, and it's always directed towards a fixed point, which is the center of the cycle. So it will be the visual image of this object N that will perform the simple harmonic motion. The visual image of what object M that will be performing the word simple harmonic motion. Here will be what theta. So the visual image of M that will performing the simple harmonic motion along line BE. Please note, it performs simple harmonic motion along line BE. So here we are having the radius of the cycle, which is usually equal to the amplitude or the maximum displacement of the object from the center of the cycle. Please note, here we are having the radius of the cycle, which is equal to the amplitude and equal to the maximum displacement of the object from the center of the cycle. And now this is what the angular velocity with which the object is moving around the cycle. And note here we have an arc. The arc created by the real image, which is when moving around the cycle. We have an arc here, and we call the arc here S. We have an arc here, I'll call that arc here S. This arc is being created by the object when moving around the cycle. So you agree with me here that angular velocity, this is angular displacement theta here. So you agree with me here that angular velocity here is equal to angular displacement all over time. Know that theta here is measuring in hours, time here is measuring in seconds. So from here we can see theta here is equal to WT. Let's call this our equation now. And this is okay now. Now, what is the length? Well, we're having an arc here inside the motion. So what is the length of an arc? Length of an arc is equal to theta all over 2 pi. No, pi is equal to this pi as seen here is equal to 180. This is an angle pi which is equal to 180 rads. Because of what 180. So 2 times 180 will give us what 360 times 2 pi r. So at here this one goes off and S now is equal to what theta r. So let's make this as well as a formula. We divide both sides by r. So theta here is equal to S all over r. So this, let's call this our equation 2. So let's substitute the value of our equation 2 back into our equation 1. So theta equals to wt, which is our equation 1. Let's substitute theta. You are going to be having s over r equals to wt. S over r equals to what? Wt. So let's divide both sides. Let's make angular velocity now. So into this formula, I'm going to have an s over r all over what? T equals to w. So I'm going to having w now equals to s. I'm going to having w equals to s all over r times 1 over t times 1 all over t times 1 all over t. So let's go in this diagram of. So now, sorry. So we can interchange the denominator since multiplication in mathematics is commutative. So we can also say that w is equals to s all over t times 1 all over r. So s all over t reminds us of something in mathematics, that is what velocity. W now is equals to v times 1 all over r. So v now is equals to w r. This is the maximum velocity for a simple harmonic motion. This is the maximum velocity